Welcome to this evening celebrating the winner of the Abelprijs 2024, Michel Talagrand. And welcome to you who are here present, to the people who are present online, and especially to our three speakers. So thank you for coming to Amsterdam and to highlight the work of Michel Talagrand. My name is Frank den Hollander. I'm an emeritus professor of probability at Leiden University, and I will be chairing this evening. The Royal Academy has been hosting the Abelprijs evening since 2019, and it has become a yearly tradition to do so and to celebrate the mathematician who was awarded the prize, and also to show the beauty of mathematics. So in the next few minutes, before I will invite our three speakers to come forward and speak in their order, I will give you a brief history of the Abelprijs so that you know the background of this event, and then we will come to the three speakers. Now let's see if this works. It doesn't seem to move forward. Yeah. So the Abelprijs was established on the 1st of January of 2002, and that was for the bicentenary of Niels Hendrik Abel, who was a genius young mathematician who only made it to the age of 27, and he did some wonderful work and became very famous. And the idea was to celebrate him with a prize. And the prize is awarded by the Norwegian Academy of Science and Letters, whereas the Nobel Prizes are awarded by the Swedish Academy of Science. And the laureate of this year is Michel Talagrand, and the quotation says he got the prize for his groundbreaking contributions to probability theory and functional analysis, with outstanding applications in mathematical physics and statistics. And our three speakers are going to exactly highlight that particular aspect of his work. The Abelprijs is sometimes called the Nobel Prize for mathematics. And the reason is that in his will on the 27th of November of 1895, Nobel stipulated that there should be an annual prize in 5 areas: physics, chemistry, medicine, literature, and peace. The Peace Prize has a somewhat different flavor, and mathematics was not included, and you can speculate about why that happened. That is a fact. And the Abelprijs was started, and it had a bit of interesting history. It was the Norwegian mathematician Sophus Lie who wanted, for the first centenary of Abel's birth, establish a prize in his honor. Unfortunately, he died 3 years before that moment happened, and somehow things fell a little bit quiet. In 1902, at the century celebration, it was King Oscar II of Norway who actually started to take an active interest in making this happen. But things did not move on, because the dissolution of the union between Sweden and Norway in 1905 put an end to the plans, and everything was sort of lying dormant for a very long time. And with Abel's bicentenary drawing close, the Norwegian government established an Abel fund in order to establish also the Abelprijs. And in fact, the first Abelprijs was awarded in 2003 to Jean-Pierre Serre. Today's speakers are, and I'm going to introduce them in more detail later, are Alice Guionet from the École Normale Supérieure de Lyon in France, Anton Bouvier from the Bonn University in Germany, and Aad van der Waard from Delft University of Technology in the Netherlands. And they are going to each highlight a particular aspect of the work of Michel Talagrand. So Alice, can I invite you to come forward and deliver your presentation. I'm going to say a few words about Elise. So Elise has worked, among others, on topics that involve disordered systems, spectra of random matrices, concentration of measure, Gibbs theory, and also spin glasses. And what is interesting in particular here is that Elise was a member of the committee who awarded the Abelprijs 2024 to Michel Talagrand. So she has a particular personal close view on Michel's work, and she will in particularly highlight the aspects of Michel's work on concentration of measure, and the tantalizing title is How Lots of Independence Can Lead to Little Randomness. Please.
Thank you very much. Thank you. Is the sound okay? Yeah? Okay. Thank you for the invitation to give this talk. So maybe I should start by saying that one of the letters I read about Michel Talagrand was saying that Michel Talagrand was the mathematical hero of this researcher, and I think I share that in the sense that the work of Michel Talagrand is omnipresent in my own work and many works in probability today. And yeah, I will talk about concentration of measure, and this is a tool which I use very often. I was wondering if it was in all my papers nowadays, but at least half of them. And we will see that this is kind of a phenomenon related with concentration of measure. So what is concentration of measure? The idea is that somehow if you have a function of random variable, a priori it's a random variable, but if it's a smooth function and you have many random variables, actually very often it will be very close from its median or its expectation. So it will not be random anymore. Somehow you have this strange phenomenon that the more random variable you get, the less random you are. So this is what I want to explain to you in this short presentation. So I will start from kind of the basics of probability theory, and which is quite related to this phenomenon of concentration of measure. And it's a question of what happens when you toss a coin. So you can ask if you toss a coin once, so is it going to be tail or head? And if it's a fair coin, I think we will all agree that it should be head with probability 1/2. And so you have no way to predict really what is going to be the outcome. But of course, if you throw your coin 100 times, then you can start to predict at least the number of times you expect to see heads. And this will be a non-random event. You expect to see heads half of the time, approximately. Okay, and so all the questions in probability is to say, what does it mean approximately, and how can you modelize all these things? And so the answer to these questions was given a long time ago by Bernoulli. So you can imagine that your coin is modelized by a variable which is either 0 if it's head, for instance, or 1 if it's tail. And if you want to look at the number of times you have tails, well, this will be the sum of your random variable. Okay, and then you ask what is the average of this number, and what Bernoulli proved a long time ago, it was in the 17th century, he proved that if you look at this number, it will be approximately equal to n/2, and the error will be at most of the order of the number of random variable. Okay, so here I wrote that. No, I made a mistake. Yes. So I wrote it there. So the probability to get between n/2 minus an and n/2 plus bn success with n independent trio or toss of coin converge to 1 as n goes to infinity as soon as A and B are positive. Okay, and so the proof of that was really based on combinatories and counting the number of occurrences where you have this event that you have and between n over 2 minus n and n over 2 plus bn success. Okay, so that's the first answer, but you see that you have still many questions. So is the error that you are giving here sharp, or can you improve it? And also, how big has to be n so that you can say something? I mean, here you say n is going to infinity, but that's very vague. So how n should be so that you have this type of result? So the first question was about the error, and this was also tackled a long time ago by De Moivre. And so De Moivre showed that the error is not of order the number of trials, but of the order of the square root of the number of trials. Okay? So if you want to look at the number of times that you have heads, it will be of the order of n over 2 plus or minus a square root of n. So it will be in this interval. Okay, so the error is of order square root of n. And moreover, if you renormalize your number of success by square root of n after subtracting by n over 2, you see that it converges to a given distribution, which is this famous Gaussian law or a bell curve. Okay, so that's kind of the prehistory or the very beginning of probability theory, but these are theorems which are very important. And you have a way to actually visualize this famous central limit theorem, which is that if you take balls, okay, in some jar, and you throw them onto these peaks, and each time a ball goes onto one of these peaks, it has probability 1/2 to go on the left or 1/2 on the right. And if you let all your balls fall down, you can see that you will have most of the balls in the middle, but you will have also some balls on the sides. And if you have enough balls, you will approximately see this distribution, which is this bell curve. Okay, and this is a picture of a real table like this, which is called a Galton table. Okay, so that's nice. This theorem tells you about the size of the error. But you still have many questions. So how general is this result? Can you take other type of random variable? And again, I did not answer at all how large should n be so that this is true. So about the question of generality, so this is a question that was asked also much before Michel, but don't worry, I will slowly come to Michel, slowly but surely. So this question was asked long ago already by Laplace. So Laplace was also one of the ancestors in probability. And yes, this is what I want to do. And so what Laplace asked was, so if I look to the regions in France, and I look at the number of boys per girls, I find some numbers. So first, there is always more boys than girls, but we see some fluctuations. And the question is whether these fluctuations are natural. You know that it's due to a statistical effect, like these balls. I mean, they're not going to be all in the middle. You will have some on the side. Or you know, for instance, the fact that you have all these boys in Jura is really natural, or there is kind of a natural drift which makes boys to be favored in this world. Okay, so that was kind of the question that Laplace asked, and later on there was also this question of if you look at the human body or many natural, or other kind of natural things in nature, so should we see that we have fluctuations which are determined by this bell curve? Okay, on this question of the generality of the central limit theorem was answered by Laplace. And what Laplace showed was that, it's here, sorry. So what Laplace showed was that if you sum random variables, which are centered and with covariance, the same covariance, say, and you renormalize by the square root of the number of variable, then it will always converge towards this bell curve. Okay, so you don't need to take variables which are equal to 0 or 1. You can take any kind of random variable. So that's kind of the prehistory. And there is still this question. So how large should be the number of random variables? And also, can we consider more general function of random variables than just their sum, so that we see the law of large number and the central limit theorem? Okay, if you take a general function in random variable, when can you say that it's going to be close to their mean, and the fluctuation will be described by this bell curve? I mean, because of course in probability theory, you don't always have only the sum of random variable, but you may have much more sophisticated function of random variable to deal with. And so this is where we see this theorem that I want to discuss today of Talagrand, which is known as concentration of measure, or also in physics like by self-averaging. And this theorem generalizes what I say and precise what I said in many directions. So first, it says that the probability that the sum of independent random variables deviates from its median is bounded by a Gaussian distribution. So this is what we say, but it's always bounded. It is true regardless of their distribution, provided the random variable are, let's say, uniformly bounded. So this looks like the theorem of Laplace. But what is important is that it's uniform on the number of variables. So it's not an asymptotic result. It's a result which is true for any given number of variables, and so which can help you to find actually the size of the number of variables that you need to get to the central limit theorem. And moreover, and this is even more important, it extends to many functions as soon as they are smooth enough. Okay, and I will describe what this means. And so I'm not going to describe this result just now. I'm also going to give some history about how it appears. And the kind of the ancient, the version of this concentration of measure result is due to Émile Borel, and is based on the law of large number I just told you about. So somehow we can think about this result as a history, the prehistory of concentration of measure, because it's kind of geometric point of view on the law of large number. So what is this result? It says, let's take the uniform law on the cube, so it's -1 + 1 to the n. Okay, so you have to imagine you are in very high dimension. You have a cube of sides with size 2, so -1 + 1. And you ask, so if I take a point at random in this cube, what is the probability that it is close to this hyperplane? Okay, so you have the distance. Distance is the usual Euclidean distance in the cube. And you look at the probability, so the kind of fraction of points which are at distance at most epsilon times square root of n. Okay, and so what Émile Borel said is that for every epsilon positive, this will be close to 1. And it's quite an easy computation when you think about the law of large number, because if you look at the distance of a point to the hyperplane, it's just going to be the absolute value of the scalar product of this point with your vector, normalized by 1. And so when you write what this scalar product is just the sum of the variables. Okay, so here you see that you will take the xi at random independently in -1 + 1. So this is a sum of independent variable uniformly distributed in this segment. So you can use the law of large number, so the one which generalizes Bernoulli to uniformly distributed random variable. And what you see is that this probability is just the probability that this renormalized sum is is smaller than epsilon, and this goes to 1. Okay, so that's a very easy result once you know the law of large number. So, but the real start of the concentration of measure, the place where people say, well, this is really the first result about concentration of measure, was due to Paul Lévy, so shortly afterwards. And he has kind of the same type of result, but this time on the sphere. Okay? So now he looks at the sphere in dimension n, and he says, well, let's imagine I take a set which has probability at least 1/2. So if I have a point if I take a point at random on my sphere, how far should it be from this set? And the result is that it should not be very far. So if I pick some epsilon, the distance of any point taken at random from this set A should be bounded by what is a Gaussian tail. Okay, this is like the Gaussian law. And so you see that this is true for every epsilon. You can renormalize, and you see that this distance is again of order epsilon over square root of n, exactly as for the hyperplane. Okay, and so you can have a picture of that. So the conclusion of this kind of computation is that if you look at the sphere, somehow all the volume will be around the equator. Why? Because if you take the half sphere, it will have probability 1/2. Okay, and so if you enlarge it a little bit, it will have, and you look at the complement, so at the cap, it will have a very small probability. So you can suppress the two caps, which have very small probability, and you see that most of the volume is around this equator. Okay, so that's kind of the idea of concentration of measure, that somehow if you have a set which is large enough to have probability 1/2, most of the point will be close to it. So this type of result was later on generalized in a diverse setting. In particular, so if instead of the sphere you take a manifold with positive Ritchie curvature, or if you have densities which are strictly log concave, but this is somehow what the only generalization which could be made before Michel Talagrand arrived. Let me, before I go to the result of Michel Talagrand, the suspense is getting quite strong. Let me just show you that this concentration of measure on the sphere had a very important consequence, which is that Paul Lévy already remarked, which is that in high dimensions, functions which have small oscillation, so basically which are Lipschitz, are almost constant. Okay, and how do you see that? Well, here I start to have some mathematics, but okay, we'll have several slides like this, but they will be almost identical. So maybe I spend some time on the first one, and I will just show you the difference later on. So I take a Lipschitz function, so for the Euclidean distance. So this means that this is a function from here, so it's a sphere, because this is a result of Paul Lévy, but it could be Rn. And I assume it's Lipschitz, so if I take 2 points and the difference, then this is going to be bounded by the Euclidean distance between the 2 points, up to some Lipschitz constant. And so the median of f is the smallest of the t, so that the probability that f is greater than t is smaller than 1/2. Okay, and so if you use this result of Paul Lévy, you can see that the probability that this function of this variable minus its median is smaller than the Lipschitz constant time eta. So here eta is any positive constants. This is going to be bigger than 1 minus 2 exponential minus n eta squared over 2. Okay, and it's easy to see how to deduce this result from the previous one, because if you take A to be the set of X so that F is greater than MF, it has probability greater than 1/2, and so you can apply the previous result. And you can then change also f into minus f. Okay, so you get this, this result. Oh. Not yet Talagrand's result, but okay. It will be the next slide, I think. So Talagrand was really motivated to study this concentration of measure phenomenon due to the work of Millman, and he's saying it explicitly in many places. Because Millman showed the importance of concentration of measure. And in fact, he understood that it could be used not only in probability theory, but also in geometry. And this is what Gromov highlights here. And this was kind of a big advertisement to study concentration of measure. So what did Millman prove? So he gave a new proof of this Dvoretzky's theorem. And Dvoretzky's theorem is a bit like also geometry in high dimension. So in the sense that what it says is that so if you pick a convex body here, which is inside Rn, and then it says that you can always find a subspace of Rn, so that when you intersect it, so here, it will be almost an ellipsoid. So it will include an ellipsoid up to some homothency of 1 minus epsilon, and it will be included into this this ellipsoid. Okay, and so that was a beautiful result, which was already proven before Vitaly Millman work. But what Vitaly Millman did was to use concentration of measure by saying, well, what I can do is take f, this set with which I want to intersect my body randomly, and let me show that with I can prove that with positive probability it will satisfy this. Then this proves the existence. And to do that, he used a concentration of measure. So to prove that with positive probability, he had a nice way to find this hyperplane, this subspace F, and he could prove like this that this hold with high probability. And then he was trying to convince everybody to study concentration of measure, and so this is what Talagrand did. And this is Talagrand's result. So I wrote 95 because so at this point Talagrand wrote a very big article which he published in Publication l'IHES, which was about 200 pages or even more, so maybe 300, so it was like a book. And one of the results was this result, which is exactly the set. It's much more general. So what Talagrand does is not taking a point on the sphere, but is taking independent random variable, and he just assumes that they're bounded by some k. He takes also some smooth function f, and then he gets exactly, so also Lipschitz as Levy, and then he obtained exactly the same bound as Levy. So from a result in a very specific case, which was the uniform law on the sphere, he could derive a result which does not even depend on the law of the variables, it just depends on their bound, which is here, k. So this is a very strong result, which is used in many settings. And so if I come back to the question I was asking before, if you apply it to the sum of your variable, which was for the coin toss, so it was the sum of variables which are 0 or 1, then you can use this inequality of Talagrand. You can compute the Lipschitz constant, it's about square root of n. The median is very close to the expectation, so I gave a very rough bound that you can also deduce actually from a Talagrand inequality, and you see that the probability that this sum is away from n over 2 greater than that the error is of order greater than t times square root of n is bounded by a Gaussian tail. So that's a very precise result, which is true now for every n. But as Lévy, Talagrand had a point of view which was much more geometric somehow. And what he said is that the concentration of measure phenomenon, so in the project space, roughly states that if a set A in this project space has measured at least 1/2, most of the points are close to A. Okay, so it's exactly like in this result of Borel and Lévy, but in this generality. And the statement that he obtained in this paper of 95 is exactly this one. So again, he looks now at this product space on product probability measure. He takes a measurable set. And what he says, so he does not need to assume that the probability of A is greater than 1/2, because here he's multiplying by this probability, and he says that the probability of A times the probability of the complement of some enlargement of this set will always be bounded by the Gaussian tail. So one of the big points in this article, I will not go into details, but was to choose the best distance to do that. And one of the distance that Talagrand picked is this distance, which is called the convex Talagrand distance, which is one of the nice distance to pick to get such a result. Oops. So this time, oops. Yes, I did it too fast. Okay. Yeah, I have problem with this. Okay, so just to conclude on this, you can again find the previous result by taking A to be this set where F, your random variable F, is greater than MF. Okay, so this result has billions of applications. As I said, I think I am using it in most of my paper. It's very useful in statistical physics, where you have probability measures with many random variables, and where it's important to know what is random or not. It was used by Talagrand in his monograph on the free energy of spin glasses, where he could prove that the free energy that Anton will talk about, so the free energy of spin glasses self-average. He could even show in this monograph that, in fact, not only the free energy self-average, but also the partition function, when the temperature is high enough. It is used in random graphs. It is used, so I'm working on random matrices, and I use it a lot on random matrices because the spectrum of random matrices are smooth function of the entries. It is used in computer science and many more. And here I just took the picture of a few books, as you see in statistics, in coding and algorithms. And so this is just, this is a book on concentration of measure. Okay, so I think my time is done. And so thank you for your concentration.
So thank you, Alice, for this very nice presentation about a beautiful gem in Michel Talagrand's work. I will ask the audience to keep the questions for later, because after the three talks, the three speakers will form a little panel, and then we will dive into the questions. So, Anton, I would like to invite you to give your talk. So, Anton Bouvier is from the Institute for Applied Mathematics in Bonn University in Germany. He has worked on topics including disordered systems, metastability of interacting particle systems, branching processes, and also on spin glasses. And he has made very interesting excursions into mathematical biology, also a very exciting field. He has over the years very closely followed the work of Michel Talagrand on spin systems, and he's going to be talking about the groundbreaking contributions that Michel Talagrand did in this area. And his title is Michel Talagrand and the Wonderful World of Spin Glasses. Please.
Yeah, thank you, Frank. Thank you for the invitation to talk about some aspect of this work of this true hero of mathematics. I perfectly agree with the statement that Alice made. I mean, he's a remarkable person, and I come back to that. And we will talk about spin glasses. Now, spin glasses come from physics, and we will start with a brief history of the history of spin glass, and it started essentially in the 60s, 70s with experiments, physics experiments, with in solid-state physics, with measuring magnetic properties and of alloys, of ferromagnets and conductors in particular. And Canella and Mirosh in 72, I mean, they worked on gold mixed with iron. Now, why do you mix gold with iron? There's actually relatively little iron in the gold, and but they came up with the idea that these strange properties, which I will not explain in detail, but strange magnetic properties, should be attributed to the fact that the iron atoms, now iron is a ferromagnet, so it's like a little magnet, and which are diluted in the gold, right? And that these positions are random, because we are just we take a small concentration, throw it in, and then we are just random. And then we had this idea, or we stood that basically this interaction between these magnetic moments of the iron, they should be modulated by the conductor. Gold is a very good conductor, so that depending on the distance they are either attractive or repulsive, right? And so that gives this idea that there is a strange behavior due to randomness and due to random signs of interactions. And no, it is okay. And shortly afterwards, in 74, Edwards and Anderson, so two theoretical physicists, came up with a paper which was called the theory of spin glasses. And so they put down a model that should somehow capture the features that Canella and Mirosh had described, but simplified in the language or in the setting that theoretical physics were used to, namely kind of settings of lattice models, where you place spins on a regular lattice. And then we said, well, okay, but these spins, they have attractive or repulsive interaction, and we put them just as nearest neighbor, but with random signs and random strength, right? So, and that should give this model. And we wrote a nice paper, which caused a lot of interest, but it was somehow, very, very, very hard. And we will talk about this. And in fact, as I mentioned, still nobody really has understood the behavior of their model completely. Even in physics, it's disputed. But when there came and that is sort of our real starting point, when there came the Shanken and Kirkpatrick, and they made it even simpler, right? Like physicists always like to make things simpler, right? And making things simpler is to go back from the Ising type model, where Ising said, spins interact with their nearest neighbors, forget about the geometry and go back to Curie-Weiss. So it's about 19th century, they say, well, every spin interacts with each other in the same way, but with random strength. And I will come back to that model in more detail. It's just sort of now part of the history, right? So that is basically became known as this famous Shanken and Kirkpatrick, or SK model, that we will mainly talk about in the connection with Michel Talagrand. And it was called a solvable model of a spin glass. And they solved it, except that the solution was wrong. We'll come back to that, right? And 5 years later, Giorgio Parisi, come back to him also in more detail, he came up with a correct solution from theoretical physics. He wrote a paper called A Sequence of Approximated Solutions to the SK Spin Glass, where he somehow corrected the mistakes or the simplifications made by Shanken and Kirkpatrick. And I come to that in more detail because this is the whole story. And then, 2004, just 24 years later, Michel Talagrand wrote a paper called The Parisi Formula. And this paper proved mathematically rigorously that this solution of Parisi was correct. So here's just a few pictures of these early measurements of magnetic susceptibility, resonance magnetization. So we have this kind of real physics. I just want to show this comes really from physics. And Right. So now we should go into more details, and we start with the SK model. So here are the two gentlemen, David Shelton and Scott Kirkpatrick, and they wrote this paper, Solvable Model of a Spin Glass. It's always funny to read that title at the time, right? Because they really thought it was very simple. But this, okay. So when this model was there, and it's in the abstract, if you want to read it, you can say, that is precisely what I said. You have these central spins, we interact with Gaussian random variables, and actually it looks like that. Right? So what is it really, this model now? Right? What is this model? And now we formulate it purely in mathematics terms, and that is important because that's why Talagrand got attracted to it. So the SK model is basically given by a random function, which physicists call Hamiltonian, on an n-dimensional hypercube. Now it's the same -1, 1 to the n that Alice had on her first or second transparency, right? Except that the n is a capital N, but that is a matter of taste. And so this is a function that depends, that lives on this 2 to the n, there are 2 to the n points in space, in this spin space. And it's given in a very simple way. It's just the sum of the products of the sigma I, sigma j, times something else, namely times the independent standard normal Gaussian random variable. These are the same, the Gaussian random variables that Alice had in her talk. Right, so, and when you sum all this stuff up, and this is supposed to reflect in physics terms the energy of such a alloy, with respect to the interactions between these magnetic moments, these ferromagnetic atoms. And normally we put a 1 over square root of n, never mind. Right. Now, what are the questions? Now, so, this is a random function, so we are talking about random functions, just in the same way that Alice said that Talagrand was used to look at functions of independent random variables. This is a function, right, of random variables. What are the random variables? Where these, sorry, I just got that the wrong way. These are these Jij, right? So the idea is you should fix these Jijs, we take them, you pull them somehow, and then you have a function on this -1, 1 to the n, these sigmas, right? And now we want to know what does such a function look like? What does it mean? Well, you can ask lots of questions. The simplest question is, what is, let's say, the maximum, right, of the maximum of all the spin, all the positions, all these sigmas of such a function takes. Now, this is, of course, again, random because it's, because you have a j sitting in there, the j, these are these independent random variables that sit there, and you would like to see how does that behave. And this is a classical, the question which is very traditional in this country, because in this country the theory for extreme value statistics was invented for very good reasons, namely in order to understand how one should build dikes, right, in order to actually anticipate maxima of, in that case, like tides, but it's just a function of of randomness. And so if in the simplest case, when this h sigma were just independent random variables, then this would be covered by the classical theory of extreme values. Right? So in physics, people are looking at an object that is traditionally looking at an object that is a bit different, but actually related, which is called the free energy. And what you do there is you say, well, I take this random function, I take the exponential of it, I multiply it for good measure by a number which is called the inverse temperature. And then I take, instead of, let's say, the maximum, I just take the sum over all these values, all the sigmas in these values. And then we take the logarithm, and then we take the mean of that, and then we divide by beta n, no matter, and take the limit as n goes to infinity. And then if they could compute this, they would be all very happy. And you can see there's a relation to that if you want. If you take beta to infinity, then this thing will actually converge to the maximum of this function h. Right? So, but it gives you a little bit more information, and that is sort of the holy grail in statistical physics, that you would like to compute these free energies. It's some classical thermodynamic object. Right, so that's what you want to do. And now how do you do this? You see, you want to take this expectation of a logarithm of a sum of exponential things, right? And you say, well, yeah, if I can take my expectation, now then the randomness goes away. So clearly this thing is not random because I take an expectation. But it's kind of difficult to take an expectation of a logarithm of something. And because it's a nonlinear function, don't know how to do this. And again, physicists, actually not physicists, but Mark Katz had this brilliant idea how to compute the expectation of a logarithm. Right? And that is called what I would call the ominous replica trick. And the idea there is very simple. You say, well, I want to compute x to the n. Right? So if I take x to the n, that's nice because it's a power, that gives you moments, so that would be nice. And now I say, well, x to the n, that's just e to the n times the logarithm of x. And so it's just this. And now I can say, well, if I subtract 1 from that and I divide by n, right, then I get back the logarithm of x if I take, if this approximation becomes exact, if n goes to 0, right, because this approximation e to the n log x is 1 plus n log x, you have to take n to 0, so I have a way to compute the logarithm from a power, the nth power, right, I have to compute this. And now if I want to take the expectation, that's easy, so I do this trick for the function whose logarithm I wanted to compute, namely the sum over sigma e to the beta, my Hamiltonian. And now I take this to the power n. That's easy. I mean, you just take a sum to the power n. You can do this. You can write it down. It becomes an n-fold sum. And in the sum, there appear only things like e to the beta, then with jij, and then a bunch of sigmas. That's, again, a Laplace transform that we can do compute, particularly for Gaussian random variables. You do the computation, and you get out an expression which is now just a sum over sigmas, e to the beta squared times some sum, again, ij, and then a bunch of these sigmas. So it's a nice, perfectly nice expression. Looks like a model without disorder, just like a statistical physics model without disorder. And then the physicist says, oh, that's brilliant, we can do that. We can actually compute now for this thing, we can compute the, well, we take, or whatever we take this nth power, we subtract 1, we divide by n, everything will be just fine. Now, the only problem is, this computation that I showed there, this computation here, it only works if n is an integer. A positive integer, actually. So it's 1, 2, 3, 4, 5. It's perfectly fine. But how do I take an integer to 0? Right? So that's worrisome. So physicists usually don't care. I mean, they just do some computations. They hope they get something out that depends on n, and then they take n to 0. And that has been exactly what Schenken and Kirkpatrick had been doing. Now they had some way to actually look at this object, and they take, oh, okay, fine, gave a wrong answer. Right? They gave a wrong answers because of the following reason, because if you look at the object that we computed, the solution that we computed, it was in contradiction with elementary physical principles. It produced something of negative entropy, so never mind. So it was known that it was wrong. But then there came this gentleman, Giorgio Parisi, and he wrote this paper, as I already mentioned. And he said, it's easy, it's very easy to do that. I can do it with a nice Italian accent. It's easy. Take n, instead of taking it to 0, you just take it to infinity. Yeah, that's always the same thing, 0 and infinity. And then you introduce these infinite dimensional 0 by 0 matrices of a very particular structure. A particular structure, I've tried to make a sketch here, that somehow where this is supposed to be a 0 by 0 matrix. Right? Yeah, but it's infinite dimensional, but never mind, and then if you do this, say, okay, I can get it. Now what do you get? So he gets an answer for this free energy. Free energy is given by some infimum of some function, right? Psi here, and the Q over which you have to take the infimum is just the set of all probability distribution functions on 0, 1. These probability distribution functions on 0, 1 actually parameterize these infinite dimensional 0 by 0 matrices. Right? Wonderful. And this function zeta, right? That is actually a solution of a partial differential equation, which also involves with Q. Right? So that's nice. So you say that's a solution. And so apparently this is maybe not true, but it sounds nice, is that when this paper was submitted to a journal, there was a referee report that said this work is not worth a paper it is written on. Because it was, I mean, the construction was looked so crazy, and what I told you probably should think it is completely crazy, right? That's completely rubbish. But right. But after some time, this was accepted in physics because they somehow, physicists thought they somehow understood what was going on, and moreover, it gave always the correct answers. It could be applied to different things, and so well, let's just believe it. It sounds nice. Yeah, but for mathematicians, it was somehow, a nightmare. Actually, when I was a PhD student, my advisor gave a problem to a new arriving postdoc and said, take these papers by Parisi and make it rigorous. And when he disappeared for about 5-6 weeks and wasn't seen, came back with blue eye, very pale, and somehow and asked, what did you do? I said, Jörg told me I should make these papers rigorous. I couldn't understand a word of what was written in there. Right? Okay, so that was a situation. It remained very mysterious until in 2006, our gentleman, our hero today, wrote a paper which I said, the Parisi formula, and it says, using Guerra's interpolation scheme, we compute the free energy of a Schergen-Kirkpatrick model for spin glasses at any temperature, confirming a celebrated prediction by Parisi. Right? Now, yes. So that was not done in a day. It started at least 10 years earlier, roughly at the same time when the second paper of the FIG papers on concentration of measures appeared. It was actually in the paper New Look on Independence. And Talagrand enters the world of spin glasses. Now, there was a background to that. Background was a book by Michel Talagrand and Michel Ledoux called Probability in Banach Spaces. And at the time, we were working on a sort of related model, the Hopfield model with Pierre Picot and Véronique Guérard, and we came across this book. And at some moment, I remember we were sitting in the office and said, well, this book really has all kinds of stuff which looks extremely useful, but it's terribly hard. But he said that if this guy ever starts to work on spin glasses, then we can just stop. I mean, he will just do everything, for us. That's just the end of the story. And this is what he did. And he had this, right? So what did he have? He had concentration of measure, as Alice explained. It's an enormously important tool to do any of these computations. And he had, of course, this background in analyzing extremes and regularity problem of high-dimensional stochastic processes. Now, you see, in my opinion, there was always work on high-dimensional stochastic processes and their extremal properties and so on and so forth. And people were working, also Talagrand, they were working with the tools that they had in which constantly improving things. The big thing that happened is that there was one particular random function, namely this SK Hamiltonian, which was simply there. And then Talagrand saw it, and he was in a way, I think, a little bit shocked that he couldn't solve it immediately, because it was actually difficult. It was a very particular, it didn't have all the properties that you would like to have. And so he started to work on that. And what he brought was a lot of energy. And a lot of energy in order to actually go about and start to look at this thing from angles where he could see what was going on in order to actually move on. And so I like this citation from his book. It's rather paradoxical for a mathematician like the author to see simple basic mathematical objects being studied by the methods of theoretical physics. It is also surprising given the obvious importance of what the physicists have done and the breadth and the pathway opened that mathematicians have not tried earlier to prove their conjectures. Now, this last statement is not true. They have tried, but they failed. Right? So there are a whole bunch of some of us that would have clearly tried, but they simply we didn't have the energy, didn't have the tools in that field, and he then went there, and he wrote from 96 to 2003, he wrote 20 papers on spin glass models, in particular the SK model, but various variants of the SK model, Hopfield model, easy, and so on. And then he wrote this book, Spin Glasses, A Challenge for Mathematicians. And it contained basically everything he had been doing on this topic. And it is a wealth of materials. It's so much more than anybody in mathematics before him or during that time him has been doing on this model. It's just totally amazing. It was a tour de force that he got. I think he got really fixated on this. I had met him in '98, and so I've been following relatively closely what he has been doing and things. And at some moments I had this discussion. He said, "Well, how can you actually do these computations?" He said, "Well, the physicists say that this is true, so I must be able to prove it." Right? So I mean, so it must work. I just do this computation. It's very complicated. He did very horrible computations, and he said, "Why do you? I mean, he wouldn't even dare to do it." I said, "No. If it's true, it must work." Right? And that was his philosophy in this, and it was actually in the end very successful. Now, when he wrote this book, the Parisi solution is not yet in. The paper I mentioned at the beginning was not there yet, and possibly it would never have appeared if it wasn't for another person, Francesco Guerra, who is a classically educated theoretical physicist, was also interested in this topic. And he wrote, here he is, he wrote a paper, Broken Replica Symmetry Bounds in the Mean Field Spin Glass Model. And that, I would say, was sort of half the Parisi solution in a way, because he wrote a nice paper, very short paper, about only 10 pages, using quite a lot of techniques that Talagrand knew very well. I mean, too, but he had the brilliant idea to use them in the right way, and he showed that not that the proposed solution that I showed you that Parisi had for free energy was an equation, but he said it's an inequality. The actual free energy is, I don't remember, it's larger or smaller. I think it's smaller than that. And so then there was only the half of the work to be done, namely to prove the opposite inequality. And this was something that I think Guerra could not have done, that nobody probably at that time could have done. And Talagrand, when he saw this, actually when I saw this paper also thought maybe we should try to prove the opposite inequality. I said, no, it's not worth it because Talagrand will do it. It was completely clear that he did it. He wrote a 50-page paper, appeared in the Annals of Mathematics, that contains a complete proof of this other half of the result, namely the lower bound, and it established the existence. And that is his comment on Guerra. It is impossible to recommend too highly the reading of Guerra's papers. And that is true, because it's a very insightful thing. So it's also nice because it's a mixture of. I think the advantage that Guerra had was he had some more better physical insight in the interpretation of this Parisi solution. Right? So you got this. It's not just getting this bound, but it's also getting a particular way of describing it. And then Talagrand had the technical tools, the technical strength, and the stamina to actually complete this. It's an amazing thing. Now, you can say, well, who cares, right, about this SK model? Actually, my advisor once asked Talagrand, you're a brilliant person, but why do you work on such uninteresting problems? I'm not sure what Frank was. Yeah, we were there. It was in Cortona at the breakfast table, and then Bernard de Ridi said, maybe it is not that uninteresting. But it's actually more than that, because it's actually a paradigm. So this is just one model. It's a highly correlated, high-dimensional Gaussian process. And the methods that are established to solve it, which were established by Talagrand and around Talagrand in order to do this, can be applied and have been applied to many other things. Right? So it's just an example, but it opens toolboxes for studying other problems which are not at all related necessarily from physics or from spin glass theory, but neural networks. That was one of the early things. That is something I have been working on at the same time, a Hopfield model, perceptron. In computer science, it was a big thing, satisfiability problems, KSAT, assignment problems. They fall into the same category. Typically, this type of NP complete problems are connected to things which are similar to things. In data science, for instance, the Grothendieck problem, which is also a maximization problem of nonlinear. It's not really random matrix, but it's higher powers than random matrix. That was recently actually solved using precisely this spin glass approach of Talagrand. In data science, deep learning, understanding, you see this function, this Hamiltonian, that could be not just, this is a particular example of a random function, but it could be, you could think of it as data, right? And you want to find some minimum in that, or you want to have some information you want to look for in deep learning, you want to find minima of other structures. And in all these problems, they become very difficult, and this work of Talagrand opens tools to work on this, and this has been done and is being done as we speak in a variety of concepts. So thank you for your attention. And so the interesting thing again, I think, is that in the distance of 3 years, for the same problem, a Nobel Prize and an Abelprijs was awarded. And this is a conjunction of physics and mathematics, which is extremely beautiful. And for the younger people, many problems around spin glasses are still completely unsolved. In particular, with what I mentioned earlier, this model of Edwards and Anderson that we go to appears, they still don't know anything about it. I wrote, it's part of my PhD thesis is about this model, and we didn't actually prove anything really at the time. But nobody else has really proved anything reasonable in the time since then. So this is still a fascinating field. It was a great field to exercise mathematical power for Talagrand, and he has really brought an enormous push to one field. So that's all I wanted to say. Thank you very much for your attention.
So thank you, Anton, for this beautiful story where you say you climb a very high mountain and there's some crazy things happening along the way, but the peak, at least, was always in sight, and finally people got there. So that's a wonderful lesson for all of us. So Aad, may I invite you to come forward. So our third speaker is Aad van der Vaart from Delft University of Technology. Aad has worked on many problems, including empirical process theory, non-parametric inference, Bayesian statistics, infinite dimensional statistical models. And he's the author of several textbooks in statistics, but not only that, he has also worked very extensively with people in other disciplines, including the life sciences, epidemiology, and econometrics. And he's going to highlight the impact that Michel Talagrand's work has had on statistical learning. And his title is Michel Talagrand, Empirical Processes and Their Application in Statistical Learning Theory. Aad, please.
Thank you. Thank you, Frank. Yes, my team basically is Michel Talagrand and maximal inequalities, but I'll hang it up on applications, and one typical application may be the central application in statistical learning, or machine learning if you wish, which is to learn a system, an input-output system, which is just a map that takes an input x and then cranks out some output y, and y is just some f0, some function of x, you would say. And we want to learn this system from some examples, xy, x1, y1 to xn, yn. You can see it illustrated in these three pictures. The system we want to learn is visible in the left picture. That's just this graph. Now, it's very misleading because my graph is, well, it had to fit on the screen. That's why on the horizontal axis, you see the input as just the real axis, just a number. But the sort of applications you should think of, the X is very high dimensional. Think of a photograph which is composed of many pixels, and the X is the values of the pixel, is all the pixels and the values of the pixel. And the Y here for the photograph might be whether there is a cancer visible on the photograph, or whether there is a cat in the photograph or a dog. So then becomes a classification problem for photographs. Input very complicated, and we want to learn how the outputs Y depend on these inputs. We get some examples, which are the blue crosses in the second picture, which you see overlaid over the graph. And you see they're not quite on the graph, and that's why I call them noisy examples. They're not exact. There's, in many applications, almost every application, there is some noise, and so you have to take that into account. What you get to see is in the third graph, and the problem is simply then to go from these blue crosses in the third graph and infer the graph of the curve in the left graph. How do we do that? Well, typically one minimizes some criterion. For instance, a sum of squares, that's the least squares criterion. You compare the output Y to the input under some function f, and since we need to learn the function f, we try a lot of functions f, and then we pick one for which this criterion becomes small. Now, it would be a bad idea to make it zero, this sum, because the examples are noisy, and interpolating exactly the data points would give a bad function. So you typically minimize that over some set of useful curves, f. Or you might also put a penalty up in the criterion, add something to the criterion that avoids to get a too wiggly f that might be interpolating the function. Or maybe you change the criterion somewhat and get something more general, something that we call a loss. And that's not going to be any importance for the talk. It's just that we will minimize some criterion to get some f. The f could be all kinds of things. It classically might be a set of polynomial functions, lines or higher order polynomials. In the 70s, it were things called Vapnik-Savounenkis classes, and nowadays you should think of a neural network and you do deep learning. So the f's would then all take the form of a neural network, and we would find the neural network with the parameters that would fit the examples. The loss I already mentioned, there are many different types of losses, but the important thing for my talk is that the criterion that we minimize is a sum of losses. Talagrand didn't work on any of this. He actually even didn't work on this, things are on this slide, which is the theoretical analysis. However, his work is very useful when you do a theoretical analysis of such a learning method. If you want to analyze the learning method, basically you're wondering whether this method is going to work or not, then you have to make some assumptions. One assumption is very often made, and that is that these examples that we use for learning are just not any examples, but they are in fact a random sample of examples from some population, say. So random, that means they are independent. That word has already been mentioned a number of times. That means we do not sample the same examples several times, or we do not sample in the neighborhood of other examples, but we really take independent samples. And random also means that it is unbiased from some population. That's important because then we can use something called the law of large numbers, going back to Bernoulli, as mentioned by Alice, which says that the average of now independent random variables converges to the population average, which I have here denoted by the letter E. The E of the loss is the expected loss, and that is just like the population average. Over all examples, you average it out. That is, as the number of samples goes to infinity. We're going to analyze whether this method works if the number of samples is really large, or mathematically we will look, does it work as n goes to infinity? That's one assumption. Then the second assumption, or you might also say maybe that's the definition, is that the target function that we're after, the f0, minimizes this population average, which I called m of f. In that case, if that assumption, if these two assumptions are true, we may hope that the data-based procedure that gets this f hat and minimizes the empirical, it's called, criterion, that will tend to the minimizer of the population minimizer f0. And that's a bit boring, because that is usually true. Yeah, I really have to make a silly choices for all these objects for this not to be true. The interesting question here to ask is, how fast will this f hat converge to this f0? And to have some idea on how you could answer that, look at this picture. This is the m, this is the population average. Very misleading picture, which I drew as a parabola. Now on the horizontal axis, there are all the possible f's. And the f's will actually be functions, so it's a misleading picture in that way. But what is sending the right message is that we are minimizing something, and there is a point of minimum that is this f0. And we will think of the horizontal axis still as something that if you move away from f0, then the criterion that we're trying to minimize is increasing somehow quadratically in some distance measure on this set of f's. Then that is the population curve. What happens when we use the data examples to get our real procedure that we're really learning? Well, the MN, that is the empirical criterion, is going to look like this population average, and that's why I drew it here as this red curve, which is a bit wiggly because it's random. There's based on these sample values. This is for one particular value of the samples, this red curve, and the minimum of the red curve is the f hat, and it's not the f0 in my picture, and that's typical, and that is because the red curve is not the black curve. But we're interested in how far is this f hat now from the f0. And clearly that will depend on how close the red curve is to the black curve. And that's the difference that I put in a formula there, MNF minus MF. I also multiplied that by n. That's nice for my later formula. But the important thing is here, this distance between the red curve and the red and the black curve, because the f hat is only not equal to the f0, because the red curve has this fluctuation down here, which makes it smaller at f hat than at f0. And the black curve did go up at that point f hat. So how fast is a question you're going to answer? You can answer looking at these differences between, the vertical differences between the two curves. And in fact, better, you look at the maximum deviation. Suppose that this distance here between f hat and f0 is about delta. Then look at the maximum deviations between the two curves in that neighborhood of that size. And that is measured in this phi n hat here. This is the theme of my presentation. That is this maximum. We're interested in here in a maximum of these random variables. The random variables here are the vertical distances. We need to look at the worst case of the distance because the f hat is looking at the smallest value of the random criterion. There is a theorem that looks like this. If this fluctuation function is at delta n equal to delta squared, and the square here comes from the fact that I made the population version in a parabola, then the distance between the f hat and the f0 is of the order delta. So we need to solve this equation here, which comes from this maximal inequality, to get to an answer to this question, how fast this is. And this is a bit of Dutch pride, because this is a very well-studied problem, and it has been studied in many cases and different setups and many variations. But I think you could say that it starts in the setting with the thesis of Sarah van der Geer in Leiden in 1987. So it's that old, but it's still active in new settings like neural networks, which didn't exist at the time. But for this talk, the theme is that we need maximal inequality. So forget this application now. We'll just focus on objects of this type. We have a bunch of random variables. In my applications was vertical distances of empirical criterions, but just think of it as some random variable. It's indexed by t, and we have it for many t's. It's a random variable. We take the maximum, and then we want the size. The expectation sign here, you could say, that is saying, I want the size of this variable. That is very hard to get. Probabilists hate this sort of thing. Probabilists can handle sums, then you can do stuff, but maxima, nobody can compute. That's maybe the reason that we don't ask, well, how big is this? We only ask, what is the size approximately of an object of this type? You might think of all kinds of applications here. Extremes are everywhere, and so maybe this is important for these applications. But no, we're not going to do this because Talagrand didn't do these applications. We're more looking at applications like which are more mathematical and have applications in theoretical investigations in statistics or machine learning. A classical example of a maximal inequality is the maximum of Brownian motion. I plotted here the absolute value of Brownian motion, and the maximum is where it is maximal. That goes back to Kolmogorov long time ago in the 1930s. But that is very different what we need, for the reason that the Brownian motion is a simple process in the set that it is indexed by time. And now my horizontal axis that you see here is meant to be real. It's just time going from 0 to 1. These are simple objects. In machine learning, we have horizontal axes, which are all these f's, and it is something very complex, and so we need much more complicated objects. A modern example are Gaussian processes, and I put some authors who worked on this. Richard Dudley came up studying general Gaussian processes and maxima in the 1970s, and then there was Vernick in 75, whom I mentioned, some other people, but then Talagrand, and you see several dates, so this was certainly something where Talagrand contributed a lot. And another model example is this learning example, where the random variables are the empirical processes, sum of this type, indexed by some index. In my case, it was a function f. And that also starts with Dudley. And then there are some other names and some other names that I didn't mention here. But again, it ends up with Talagrand, with several very important contributions. And indeed, this I picked up from Talagrand's website just last week. If you read that, then Talagrand will say, upper and lower bounds for stochastic processes is the topic to which I devoted a large part of my life. So it's not only that Talagrand was important for these maximal inequalities, it also goes the other way. These maximal inequalities were very important for Talagrand. He wrote 3 books on the subject, next to many papers. And it looks here as if I copied the same book twice, but actually these are 2 books. They have the same title, but they were published with an interval of 7 years, and they're very different, even though the second is a second edition of the first. If you read fast on the website that I just showed, then you will see that he talks about these last 2 books, and he says, well, never read the 2014 book because it's bad. The 2021, that is good. And that reflects sort of Talagrand's development in 7 years, that he rewrote and rethought and kept going and wrote it up and invented it in yet another way. In fact, if you would have gone to his website in 2015, then there would have been a similar message. And then, of course, it was about the 2005 book. Rubbish, this book. In fact, more interesting even, he has bitter complaints there about the publisher Springer Verlag, who published all the 3 books here. And he says, oh, Springer, they refused to take this book on generic training from the market. And it's so bad. Everybody should read my 2014 book. That is really good. So it was a big topic for him. The left picture is how I know him from the 90s to, well, it's probably a bit later, but that looks like the Talagrand I know. I was actually a bit disappointed that in the announcement of the Abelprijs they took the picture on the right, which I think is, it's a little bit of a pirate. But maybe it does express very well that he was really into this and went on and on and on to make his contributions. What is that then, this maximal inequalities? Let's look at maximal inequalities and how that works. So maximal inequality just takes a bunch of random variables indexed by some parameter that I called here t, but it's just lots of variables, and maybe there's not much relation between them at first. And then we take the max, and then we want the size of that object. In fact, on the previous slide, you saw upper and lower bounds for stochastic processes. Well, those are maximal inequalities, and it's upper and lower bounds because we cannot really compute these objects. So we get an upper bound, which is you give a number that is bigger than it, and then hopefully there is a corresponding lower bound saying that it is not smaller than something, and then hopefully these two things are proportional. The lower bound hopefully is, say, 1/10 of the upper bound, and then we know sort of what the size of the object is. These upper bounds definitely go back a long time as well, and the key idea to get them is something called chaining. And that's a very simple idea. Here is my index set t that I now drew as some sort of an ellipsoid in 2 dimensions. I have to do something, but it might be a very complicated object. And I put some red crosses in, and they are sort of fine grid over this index set. I put some blue crosses, and it's a coarser set of over the index set, it's a coarser grid, and there's one black one, so that is very coarse. When you do these things, you actually go for multiple levels of this. And the chaining principle is that you take the finest, you take a point from the finest set, the red one here, and you map that, you connect that to the closest point in the right distance you have to use to one in the coarser grid, in the level 1 coarser. And you go on like this, and then you finally end up at the coarsest level, which is always a single point, and that is the black point. And every point that you have in the finest set gets a chain, and it gets a chain going to this black point. The formula I wrote here is just a telescoping formula, and that's just an easy truth. It's just saying that the difference what you have at the red one, that's this one, minus the value at the one at the black cross, that can be written as the sum of these differences across the chains. Just a mathematical truth, but it turns out that it's a very nice way of getting an upper bound for this maximum. And this goes back actually to Kolmogorov. And Kolmogorov did this for points on the line, and you don't see it because the topology on the line is so simple. Dudley was the first one to use this on a general index set, and he got a bound like this. The m here is this maximum, so the size, and so Dudley gave an upper bound, which is maybe some complicated expression. It's still very important, and it's still very well known, Dudley's bound, then it's this one. What does it say? Well, he basically counts the number of differences here of a given size. So every link, you count how many links of different sizes are there. And you count that by so-called Kolmogorov covering numbers. You take a ball of radius epsilon, usually small ball is important, and then you look how many balls do I need to cover the whole set T. That is this number that you see here. Then you take a log and a square. In fact, the log and the square are there because I'm now talking about maxima for Gaussian processes. And they arise because Gaussian processes, they have tails e to the minus something squared. That is the Gaussian function. And the inverse of that gives you a log, a square of a log. But the important thing is here to make these counts. How many increments do I have of a certain size? And you have to make that count, and then you have to add up over the different sizes of balls that you get, and that gives you a nice bound. Nice, very nice, because it's still active. It's from the 70s, and this is still one of the most used bounds if you do this theory. However, in 1975, shortly after, Wernicke, who was a French probabilist, quite interesting. Talagrand tells us about Wernicke that he was a brilliant man, and he doesn't get much credit for it. And it's true, if you go to the Wikipedia page of Wernicke, it will not say much more than that he was a French probabilist, as I just said. But this was one of his things. He gave a more refined bound, which looks a bit more complicated, and it uses the concept of a majorizing measure. The difference is a bit that this Kolmogorov covering numbers treats the T everywhere in the same way. You have one size of a ball and you slip it over the T, and then suppose you have a T which is very complex, and I gave a strange picture of this, and you need to describe this kind of structure. Maybe there are little holes and there's little extensions with these balls. That is not going to work so well. So the majorizing measure allowed you to take a mass of 1, that is, the measure is a probability measure, and to spread that over T, and then you measure the amount of mass that is in every ball. And you get a better bound. It's hard, very hard to use though. So for a long time, people didn't use it, and for a long time, people also didn't know that actually this bound is sharp, and Dudley's bound is not sharp. It's easy to come up with examples where the upper bound here is true, but there is no corresponding lower bound. It's not true that, say, 1/10 times this integral is a lower bound. And that is the first major result that Talagrand made, a major contribution that Talagrand made quite a while after Wernicke came up with the bound, that Wernicke's bound is sharp. Quite an achievement, very, very long proof. And I was at the time, 90s, present at a conference, and Talagrand got 1 hour every morning during the conference to give the proof, and that went on for 2 weeks. And it was very complicated, but very, very, very nice. Talagrand kept working on it as I kept going and going on these bounds. And he refined that proof several times, simplified it. But I also came up with other bounds that look a lot simpler. And this is the so-called generic chaining bound that still has these fine and coarser sets of points over T. But it is much simpler. You just are allowed to take sets of points, red points, say, with not too many points in it. So for every k, you take a set with not more than 2 to the k point, and then you just have to compute this sum. That is always a bound, Talagrand proved, with a really interesting induction argument. Induction is one of these ideas that mathematicians learn in their first year, and often we learn it to formalize a proof, but it's usually boring things we prove. But Talagrand has several very ingenious induction arguments, and if you follow them through and you think, okay, what am I doing here? And at the end, suddenly you have a wonderful result that you didn't see coming at all. So he got this bound, and then this is an upper bound for every set of points, but also you can choose these sets of points in such a way that it becomes a lower bound. That's in these 3 books. It's actually already in the 2005 book, which is actually a very nice book, and then it's repeated in the 2014 book, and that's also a very nice book, and then it's again in this 2021 book with lots of other things as well. Those were Gaussian process bounds. For other stochastic processes, there are similar bounds. So the Gaussian thing gives this log and this root, because Gaussian processes are like that, but this extends to many types of stochastic processes. Empirical processes, these sums of independent random variables that I have here, they are a bit like Gaussian processes. In fact, if n goes to infinity, sums of random variables are like Gaussian variables by the central limit theorem, by de Moivre and others, as already mentioned. But for finite n, you need some adaptations to get the really useful bounds. So some Gaussian bounds are valid, but to get the real useful ones, you need adaptations on that. But also that can be done, and Talagrand in his books has several refinements and has been keeping refining it. Now, my last 2 slides, I want to get back a little bit to the idea of concentration. I first recap what I said so far. We were learning some function, I called it f hat, which was a minimizer by minimizing some criterion. And then I showed you this theorem. This is exactly what I showed you before. And I said that if you have a maximal inequality, then that will tell you how big this distance is from the thing you learn from the data from the true f naught. But in many cases, there is also a so-called concentration bound in the way that Alice talked about, which would be like this. So this distance, it's a bit of the order delta n, but then concentration means that if you go a certain amount above the delta n, then the probability that it's there is very small. It's e to the minus t squared, and if t is a bit away from 0, this is going to be very small. So the distance is not only of the order delta, but it's also concentrated around this delta. So that is where the concentration inequalities come in. That's a very intellectually interesting result, but it's also useful, again, for analyzing procedures, because very often we try to use not one set of possible machines or maps, but we try many f's simultaneously. In the classical sense, you could do polynomials of degree 1, but also of 2, and why not 3, and why not 4? And if you analyze all those, then everyone will give some size here, some learning rate, but to then get the best one, you can use inequalities of this type. Neural networks is the same. And Talagrand is important for machine learning, and that one of the inequalities that is attached to his name is Talagrand's inequality. If you type that into Wikipedia, you get this one, and this is one that Alice showed you. But I think in this area of machine learning, Talagrand's inequality is usually this one. It's my last slide, which is about the empirical process. And it expresses a message that I also would like to say, that the message of concentration. It's a new way of thinking about all these objects that we didn't have before. I've been talking mostly about the maximal inequalities will give you the size of the expectation of a maximum. And that depended very much on the complexity of the T that you had. The Dudley bound used Kolmogorov entropy to measure the size of the T, or the F in this case. Concentration is something very different. This sort of bound tells you that, okay, this maximum may be small or it may be big, and that may depend a lot on this set of F's that I have here. But once you have that, the probability that the random object, so without the size indicator, E here, the probability that the random is much bigger is really small. This is, again, exponential bound. So for t moderately large, this is already very small. So the idea to separate sizes of things from concentration is also very much due to Talagrand, and that he introduced in iThinking. And that's where I stop. Thank you very much.
Well, thank you, Art, for your very beautiful expose of how the work of Michel Talagrand had a profound impact on how you deal with the very complex estimation problems in statistics, and how this led to beautiful surprises and a very deep and far-reaching theory. Okay, we've come to the discussion part of the evening. So I would like to invite all three speakers to take a seat together with me, and we're going to discuss. Well, you can ask questions about each of the three talks, and we can talk about the broader perspective of the work of Talagrand. There are two microphones in the room, so if you want to ask a question, raise your hand and ask the question, and I'll pass it on to our speakers, please.
Thank you for this three lovely talks about the work of Michel Talagrand. I would classify him as a very unusual mathematician. There are many young people here, young mathematicians as well. What can they learn from the way how he worked? What might they copy, and what should they maybe not copy?
Please.
He says that he works a lot. Yeah, I think he does that, and also I think you can see he has been working like for 10 years on concentration of measure, and then at some point he's happy and he goes to spin glasses, and then he works on spin glasses for 10 years, and then so except for chaining, I think he has been coming back always from time to time. So. Yeah.
Yeah, so I mentioned his conferences, and it was one in the United States, and well, you have the conference, and then all these talks during a day, and then finally in the evening you can have a drink with your colleagues together. And then we asked, well, where is Talagrand? Talagrand had come from France, and then the word was, oh, he's gone to bed because he's trying to keep on the European schedule so that he can keep working. Is this good or bad? I don't know.
So you have to be very tenacious. Anton, you have something to add to that particular aspect of his work and his?
No, there's well, I mean, you have to be just very clever
and persistent.
And persistent,
and stubborn.
Well, but it's true that he is working very, very hard, and I've seen him work, and I sitting next to him, and well, I say, well, I can't do that. I mean, right? So in this level, so. You don't. I mean, okay. So everybody's different, right? And he was. But in fact, what is an important aspect? This is what also Art said. He has always been working not on a tiny little problem, but on a big problem. That was sitting there, and then he goes to that direction, and he goes 10 years, and he goes 10 years to this, and. Buff, he comes out. So this is, I think, in general, of course, a good idea, which sometimes it's not so easy to do for young people, right? I mean, I think he cannot really be a role model because he's very special, as you said.
Maybe I can add something. So if you look at his interview, I think it was for the show Price, he said that so when he was young, he spent some time at the hospital because he had some problem with his vision. And then he worked with his father, and he couldn't see much. And from there, he took the habit. Well, the habit, I don't know. What he's doing, he says, is always taking a problem and trying to simplify it as much as he can. So to see really where is the point where you have to prove something in the simplest setting, and then trying to make the nicest, most general statement, to see also what is the, to apply the statement, like for concentration of measure, it's quite amazing to think that it only existed for dependent variable on the sphere. And then he has this idea to prove it in such a generality, and I think that, that's the point. He's tried to simplify the problem, but then also see it in its most general framework.
Yeah, that you have the vision to somehow open this up to a much bigger world, and then have the courage to go for it and believe that you can actually include this.
So my question is, thanks for the brilliant talks. So we have seen now like 2 Abel laureates in topics like where the probability has exponential decay. One was SRS Varadhan on large deviations, which was also about topics of probabilities having exponential decay, but we saw that it has flavors of where the result depends on the model you are studying, and Talagrand's work is much more general, like it's for general N, a very general F. So how would you relate these 2 kind of flavors of a large deviation and concentration, like together, like how they match up, and because they are quite different but still have a similar flavor? And is there a relation, or do you think there is a big future that concentrations can be improved to places where large deviations are true?
Alice, you want to pick that up?
Okay, I can try at least. Well, I think that usually what is very nice with this concentration inequality is that they are so general, so they are not optimal, they don't give you the optimal rate. But often you can use them to get the optimal rate. So, but usually it's a kind of different kind of work. So I'm not sure. So if you would like to get the optimal rate in concentration, that's a difficult question, I think.
But you would not be tempted to think, and I would not, to think of concentration as just a kind of a finite n version of what large deviation theory is doing, because there's much more geometry somehow hidden behind it. Anton?
I think, actually Talagrand once told me that he doesn't like limits.
Yeah.
Right? I mean, that in a very serious way, we just talk about the central limit here. I don't like limits. And this is really the difference, because in large deviation theory, you're always looking at these limits, right? And it's kind of a nice theory that describes, probability on this exponential level, and it gives you machinery to do computations. But it's very limited in the sense that you must have very specific properties. You must have a rate function and so on. Concentration is a much more beautiful, wonderful tool, because it works, in very, very general settings. You cannot compute the precise value, but you can actually. So, like for instance, that's also mentioned in the, in the spin glass thing. The concentration of the free energy was proven. It proved immediately it's trivial. With Talagrand's methods, but computing the value, it was much more difficult. Right. So it's a more robust tool. Large deviations are also relatively robust to some extent, but it has a different spirit and a different type of application.
So, do you also see this robustness in the statistics applications?
Well, there's a big discussion about finite n versus asymptotic results, and there's plenty of people who, in the machine learning community and in the statistical community, who hate limits also, and so this came in very useful as a tool to get finite dimensional bounds, and concentration bounds have become much more important in the last 10-15 years. Yeah.
Okay.
Does he have many students or mentees? Will he leave a school of people whom he... Yeah.
The answer is no, and he gave an explanation to that. He once said that he doesn't really have PhD students because there are only 2 types of problems that he has. The ones that the student cannot solve and the ones that he can solve much faster than the student. So he has actually very little descendants. I think he has only, in the context of Spinglasses, I know there's only one person, Panchenko, with whom he actually sort of collaborated in this context. He used to collaborate earlier with his wife when he was. I mean, that was before. I think it, in the. But he has never. He's. I mean, this is what I'm saying. He's so strong, in a certain sense, technically, that. For a student, that's very hard, and it's also his personality. I mean, if he can solve a problem, he solves it. He left a lot of open problems in his books. Yeah. Always a list of problems that people can work on, and people did that, right? But it's sort of indirect, and he has actually these multi-level problems of different levels of difficulty. And there are, of course, also young people who just pick up these problems and then go and work with them. But he has not really had his own graduate students ever, I think.
Yeah, there is also, so I think, as Anthony said, that he's passing the stick, the bâton. I mean, he's passing the stick by the books, and also by a kind of the problems he posted on his webpage. So it's a way to try to interest people. He's giving some money on problems, and that's the way he's trying to get people interested into his problems rather than students.
But passing on the stick, I mean, he like Art also showed, he has things keeps on coming back. so the stick is being passed at the very end somehow.
So, for instance, in the book with Ledoux, Probability on Banner Space, there's at some page relatively large in the middle of some very complicated proof. There's a statement that whoever has reached this place reading this can actually collect the prize if I write it well.
So that's very stimulating.
No.
No, but there was one of the prize which he gave on his webpage was solved, and he paid the price, and he gave a receipt and everything. So, really, if you look at the few remaining open problems and you solve them, you should be confident that you will receive the prize.
So this is a bit like the Talagrand Millennium Prize. Okay.
I have a question. If I were to buy one of his books, which one would you recommend?
Well, so depends on what you're interested in. If you're interested in maximal inequalities and chaining, then he would say buy his 2021 book. But I confess I haven't read that. I have read the 2014 book. But I guess the 2021. But if you're interested in one of the other topics, which are, well, they have common elements, but they are very far apart, and one of the other books, I guess.
I would recommend Probability on Banach Spaces.
So.
It's actually the most pedagogically written book, because it was written by Michel Ledoux with him, and he had, and it is actually a very excellent introduction into this entire field and the concentration of measure. It's not the latest; it doesn't contain all the latest results or so. But I mean, to get into it, I think that is an excellent source. I mean, this is also the book that I had first looked at and read partly, and it explains all the things about this background and concentration extremely well. If you're interested in, if you're interested in swing glasses, I mean, you have to buy. You may buy his. Maybe you could buy Panchenko's book. Actually, that might also be an option. But of course, it always depends.
Maybe we can explain, because somehow the point is that Talagrand he proceeds by lots of elementary steps, but he never explains really why he's going to do all these steps one after the other. So you can follow everything, but it's true that it's difficult to have the big picture from his book. But I think the article on concentration, it's not a book, but at least all the applications, they are very easy to...
The Asterix paper, this is excellent. And also the New Look at Independence, which is in the Annals of Probability. This is also a very, very well written paper. Yeah. Right.
Yeah, maybe
you don't even have to buy it, you can get it for free.
Well, and of course, his 95 paper about the concentration measure was fantastic.
Yeah.
And that's very, very tangible and very readable.
Yeah.
Let me ask a question to all three of you. So if you put everything that he does, that he has done together, is there some sort of big picture that comes out of this, or you say no, you just view it as some fantastic contributions to some fantastic areas, or do you think that you say something had to be, and he was going for it, and there's something that unifies all these contributions? Maybe a difficult question to answer.
Well, let me see from my point of view, or maybe I'm the least of it. You see, it's always about the same thing. It's always about random functions in high dimensions, and in all different aspects of it. You know, that you can imagine. And as I said, you know, there be specific examples which trigger the particular development of techniques and ideas, like this SK model. You know, which is, I mean, you wouldn't think about this model necessarily if you wasn't there from physics or somehow. But then, you know, if the whole technique and everything it develops goes around, you know, in a very broad and in particular a very general setting. So it's really, I mean, it's an amazing body of work about properties of high-dimensional random functions.
Right.
Yeah.
This is the unifying element.
Yeah, or geometry in high dimension.
Yeah, geometry of probability is the same thing, right? And this is this dual aspect that he always explains very nicely.
And now that it has that flavor too, also for you from a statistical point, that you said that's exactly sort of the common denominator.
Probably. I can take from, say, the beginning 90s, then there was this cool probability and Banach spaces where the book is also, and that there were meetings at the time that Talagrand went into. There were some people in there for a longer time, like Richard Dudley that I mentioned, and Genet and Zinn. And they said some things like, okay, Talagrand, up till now, he did some wonderful thing in functional analysis, measure theory, and he indeed did wonderful things there too before getting into these stochastic processes. And so I think it is wider what he did, but in the end it settled into these directions and the books, and where he revisited the things he had done himself as well. Yeah, I think that is true, but it is a longer, wider area that he has traveled.
Yeah. Nikos?
Nothing.
Yep. Can you hear me? Okay.
Oh,
no.
A remark that I very much enjoyed was the influence of theoretical physics on mathematics as opposed to the other way around. I've often been faced with situations where people were complaining about some problem being attacked in physics where, oh, the mathematics is terrible here and it's just, you know, completely wrong and no lower bounds or something like that. And whereas here the remark was that sometimes the problems in theoretical physics can stimulate problems in mathematics. That was very pleasing. I forget now who it was that made that, whether it was...
I think I made this remark. Yeah, sure. I mean, because it's in this particular case. I mean, as you see, I mean, it is confluence to have two Nobel Prize, I mean, Nobel and Abelprijs, you know, parallel on something, you know, that's exceptional, right? You know, I mean, usually the well, see the work of I mean, and actually, it's even true that this work of Talagrand was also appreciated by the other side, by Parisi and things. So it has a, you know, because nobody really could quite understand where this is true, and he actually made this point, and so it's a very nice confluence, which is rare, I think, in mathematics.
Actually, Parisi wrote that he didn't think that he would see the proof of his formula during his life.
Yes.
So he was very happy that Talagrand proved it.
Yes, thanks for the wonderful talks. It's really inspiring to see how concentration of measure comes back in this work, and fascinating. I really liked it. A difficult thing with, usually when I'm in the talk, my question comes 1 or 2 days later, so it's always a pity, so I'll try to formulate it as clear as I can think at the moment. I'm curious, so in other disciplines, or when we teach a first-year probability course, there are all these concepts where the central limit theorem plays a role. For example, p-values, the central limit theorem is behind it. Do you think that there are concepts nowadays, or maybe in the future, like in 10, 20 years, like daily concepts that disciplines use, where this new work will be hidden behind it?
You mean the work of concentration?
Yeah, the work of Talagrand, for example, these more heavy machinery with all these much more general concentration results on function spaces.
I think it's already used in many different domains, because again, not everybody likes limits.
Yeah.
And also it's not only a question of taste, but sometimes you really need to have finite n estimates, and this is in every domain. So the central limit theorem is used in many different domains. I mean, and so the concentration of measure as well. And I think his work is widely, very widely used. Yes.
You know, maybe to add, I mean, if you take any text or text about nowadays of the data science, you will definitely have a chapter on concentration of measure in it, right? It's and all these inequalities are absolutely crucial. So in fact, if you have more emphasis also in, I mean, people in computer science, right? I mean, they look at these things and use it. So it's a concept that enters very early. I mean, I give a seminar for undergraduate students, let's say in their second year, on some texts on data science, and then when they get confronted with this already.
Okay.
So
I have, if I also may answer this one, I have a bit more modest answer. I think this is very important for theoretical analysis of procedures, but machine learning is not going to change because of Talagrand's work. Machine learning is, for a much larger part, it's engineering and coming up with new procedures and do stuff. If then you want to compare them and know which parameters in a procedure and which variants, what might drive them, you do theoretical analysis. This is very important. But otherwise, I don't think we suddenly get completely different procedures because of concentration inequalities.
Okay.
Some of these concentration inequalities, after all, the simple ones, they are from 100 years ago, and you don't need concentration inequality on a Gaussian process to get a p-value or replace a p-value if you wish.
Ross?
Yeah, I have a question about pedagogy, actually. Do you think actually just starting with the high-dimensional geometry is a good way to teach probability and statistics?
I think it depends on the person. I'm not the one.
Yeah, there's some people who think geometrically, other things analytically, other things probabilistically or statistically. It very, very much depends on what you like. But all methods bring something wonderful.
But I think it's nice to have different perspectives. So.
Okay. I think it's time to close this evening. We could continue this discussion for a long time, but drinks are waiting for us. I want to first thank the three of you for your lovely lectures that made a beautiful tribute and a beautiful picture, not only about Michel Talagrand, but also about mathematics. I'd like to thank you all for coming and gracing this event with your presence, and that includes the people who are listening online. And I close this nice evening, and I invite you for drinks in the lounge. Thank you.